Talk about parent functions and transformations. We're going to be working on building towards mastery of this standard. And this one is talking about identifying the effects of a graph by replacing f of x by different things, which we'll get to in a moment. So by the end of this lesson, you should be able to explain how a function's graph will differ from its parent function based on transformations. So let's go ahead and look, and we're going to look at the absolute value function. So this right here is the function that matches this graph over here to the left. So when we're talking about parent functions, what we're talking about is it's the simplest form of a class of functions. For example, this is the simplest form of the absolute value function. It just says y equals absolute value of x. If we're talking about the parent function of a quadratic function, we would have something like just y equals x squared. Parent function of a linear function, y equals x. So let's go ahead and look at how this parent function gives us this graph. So over here on the left, I have a table of values, and I'm going to go ahead and I'm going to evaluate the function for these values. So this says that if x is -2, I would do the absolute value of -2, which is 2. Then for the next one, absolute value of -1, which is 1. Absolute value of 0, which is 0, absolute value of 1, which is 1, and the absolute value of +2, which is 2. These, remember, signify an ordered pair, x comma y. So if I go ahead and I go to -2, 2, this would be -1, 1, 0, 0, also known as the origin, 1, 1, and 2, 2. So if I go ahead and I were to continue in that pattern, I see that I'm getting points right there and right here. So this is the parent function of the absolute value function. Now let's see what happens when we do things to the parent function. So this is called my transformed function. So I'm going to go ahead and on the left, I'm going to make a table of values for this one. And we're going to look at what happened. So this one, if I go ahead now, I'm going to do the absolute value of whatever I'm saying my x is. And then I'm going to go ahead and add 2 to it and take the absolute value. So if I put in a -2, -2 plus 2 is 0. And the absolute value is 0, 0. If I go ahead and I change that to the next number on my list, -1, I get +1. And the absolute value of +1 is 1. With 0, I get the absolute value of 2. With 1, I get the absolute value of 3. And with 2, I get the absolute value of 4. So let's go ahead and look what happened. So now I have -2, 0, -1, 1, 0, 2, 1, 3, and 2, 4. Now knowing because it's still an absolute value function, it has to look like a V. The absolute value function has some symmetry that's vertical, which means for every point that I have to have one that's the opposite. So if I went ahead and I put in more points that were to the left of -2, 0, like -3 plus 2 would make -1. The absolute value of -1 is 1. So that's how I know I'm getting these points here. So what did it actually do? Well, the V originally on my parent function is this one, and it actually moved 2 units to the left. Now we're going to keep using that number 2 because we don't want to focus so much on the number as what it does to the graph. So let's look at what happens when we put in the absolute value of x -2 versus a +2 inside the absolute value. So I would go ahead and I would do the absolute value of -2 minus 2, which gives me the absolute value of -4, which is 4. And then if I go ahead and I change that to -1, I get 3. And now, if you go ahead and finish up for yourself, let's see how you did. Okay, and here's what you should have gotten for your table of values, and let's look at those points. So we have 2, 0, 1, 1, 0, 2, -1, 3, 1, -2, 4. And so I definitely see it's progressing this way. If I pick some points to the right of 2, 0, like 3, I would get 1, And if I picked 4, I would get 2, because 4 minus 2 is 2, and the absolute value of that is. And it looks like we have a v again. So now this time, what was the transformation? It did shift again, but which way did it shift? It shifted to the right. If it was x plus 2 inside the absolute value, it shifted 2 units left. If it was absolute value of x minus 2, it shifts 2 units to the right. And what they both have in common is that they are both horizontal shifts. But that minus sign inside the absolute value shifted it to the right, and the plus sign inside the absolute value shifted it to the left. Now let's look at what happens when we add and subtract outside of the absolute value. So again, go ahead and complete the table of values and check in. So here's what we should have gotten when we go ahead and use this function, y equals the absolute value of x minus 2. Now let's look at the graphs of those. So we have -2, 0, -1, -1, 0, -2, 1, -1, 2, 0. So notice that I'm getting that same v, which is the classic absolute value, but it's shifted down 2 units. So the function shifted 2 units down, and remember, a downward shift is not horizontal, it's vertical. So what do you think this one will do? Y equals the absolute value of x plus 2. Well, do your table of values and see what you get. So here's our table of values, and let's look at what those points give us. So here's that v of the absolute value. And so now it looks like I shifted it vertically up. So let's go ahead and stop for a second and just summarize a couple things. So when we go ahead and that value that we're adding or subtracting is outside of the parent function, it results in a vertical shift. -2 goes with down, +2 goes with up. But when that constant that we're adding or subtracting is inside the parent function with the x, it results in a horizontal shift. Specifically, that +2 causes the graph to shift left, and that -2 causes the graph to shift right. We're multiplying this time by some value, or it's basically being multiplying the whole entire parent function by a factor of 2. So let's go ahead and fill in our table of values. And there's what we get. And so when we go ahead and we graph those, so we get this, and notice that the vertex of the absolute value function is actually in the same spot. So it hasn't shifted at all. It's that point that's called the vertex is still in the exact same location. But what's changing is it actually is stretching vertically. And if we go ahead and we look at the points in comparison to where they are in the original function, okay, it's like these two. So this is 1 unit from the x-axis. So I'm looking at this value of x. For the parent function, it was at -1, 1. But for this value, it's at 2. And what happened is that vertical distance from the x-axis has increased by a factor of 2. It's twice as far from the x-axis. And that's why we call this a vertical stretch. Specifically, we would say it's a vertical stretch by a factor of 2 because the points are becoming twice as far from the x-axis. So if we go ahead and complete our table of values, pause and fill yours out, I get this for my table of values. And when I go ahead and graph those points, my vertex is in the same spot, 0, 0. I got -1.5, -2, 1, and then I have these points as well. Sorry, it's not a beautiful graph, but let's go ahead and look at those distances again. So this point right here in the parent function was at -1, 1. But now in our transform graph, notice that it's closer to the x-axis. So this point has a distance that's half a unit above, versus this one that's 1 unit above the x-axis. So it's compressed is how we call it because it's getting squeezed down towards the x-axis. So it's a vertical compression. So we would state that it's a vertical 1/2. So it's getting closer to the x-axis. Okay, last one. So let's look at what happens when we do y equals the opposite of the parent function. So let's go ahead and fill out our table of values. Okay, here's what we get for our table of values, and let's go ahead and look at it. So I have 0, 0, it's still my vertex, -1, -1, 1, -1, -2, -2, and 2, -2. So what do I get? I get what's called a reflection. And specifically, which way did I reflect it? I reflected it from pointing up to pointing down, which means it's a vertical reflection. So let's go ahead and describe all of this together. Because we don't only want to be able to do this with absolute value functions. So f of x is a function. A, k, and h are real numbers. And so we want to look at each one of those numbers and see what it does to our function. So the number a, remember, it did two things. So going back over here, a is the number that was that coefficient. Okay, and this one, it's like y equals -1 times x. So when it's negative, it reflects it vertically. Then this number either stretched it or compressed it. So we would say that a vertically compresses or stretches the function, and it reflects the function if it is negative. So let's look at this number right here, okay, that value that we're adding or subtracting from x. So here's the two cases where the value 2 was being added or subtracted from the x. So when we added 2, it moved it to the left, and when I subtracted 2, it moved it to the right. So when you're thinking about this, remember that x minus -2 is the same thing as +2. And because you're subtracting -2, that -2 is what's moving it to the left. Versus over here, -2 is we're subtracting a +2, and it moves it to the right. So when you're looking at horizontal shifts, this number, think of it as what are you subtracting from x, tells you which way to move. So it horizontally shifts the function. So let's write that down. So x minus h, let's see, if h is positive, so greater than 0, moves it to the right. And x plus h, again, if h is positive, is going to move it to the left. Okay, and now this last value, k. So let's go ahead and remind ourselves what it did. So here were those transformations where we were adding or subtracting outside of the parent function. And both of them gave us vertical shifts. And this one, when it was a minus, it moved it down. And when it was a plus, it moved it up. So basically, it kind of did what you expected. So k, in general, is always going to vertically shift your function. So if you go ahead and you think about it, it does basically exactly what it says. So plus k, where k is a positive number, moves it up. And f of x minus k moves it down, where k is a positive number. So now let's go ahead and just review. Okay, so x plus h, and again, we're assuming that h and k are positive numbers. Remember, this is going to move it left h units. So this one would move it to the right, h units. This one is outside, so it's going to do exactly what it says, vertically. So this is up, k units, and this one would be down, k units. Okay, dilations, okay, we call them stretches and compressions. So this number, if it was a number bigger than 1, 1.1, 2, 3, 4, 5, would be a vertical stretch. And this one, when it's absolute value, so in other words, it doesn't matter if it's positive or negative, but just the absolute value of it is less than 0, which means it's basically a fraction less than 1. Then the absolute value of it would always be, So then it would always give us a vertical compression. And last but not least, whenever you do the opposite of the parent function, and in class, we'll practice with this.